Hello everyone, I'm Cohen, and I'll represent to you SaveDat, a spatio-temporal trajectory compression by LSTM on behalf of ICITE orbits. According to the US vehicle registration statistics, there were 286 million vehicles that registered back in 2020. Those vehicles are core consumers of navigation services, without even mentioning the autonomous vehicles that are one step away from marketing. Besides that, these days we are witnessing a vast increasing of the usage of shipping and delivery services with real-time monitoring, which directly reflect on the emerging needs for logistic transportation and cargo shipment. In another matter, there are extensive challenges for technological companies, such as increasing cost of storage services or the continual fights over smartphone bandwidth between all those applications and cloud services. Another challenge is our growing hunger for real-time services. Trajectories are spatio-temporal records of moving objects. There are two types of trajectories: spatial, which contains only latitude and longitude coordinates, and spatio-temporal, that contain coordinates with a timestamp. When we think about trajectory datasets, most of the trajectories are overlapping, and it's very common to find duplicates of the same trajectory in a dataset, which are redundant most of the time. The trajectories patterns hold a great potential for convergence to a behavior. When we combine the trajectory's nature with the mentioned trends and challenges, the need for a good quality trajectories compression is rising. By that, we chose compress a trajectory data with the lossy algorithms while maintaining the utility of the data. While we studied previous work on the trajectories compression subject, we noticed some interesting solutions, such as conversion of roads to a graphs or a straight line network and compress it with a lossless data compression algorithm, or separation of the trajectory data to components, a spatial data and a temporal data, and compress each component separately. We even ran into a work that suggested to omit the temporal data, which people may say is a waste of data. Besides that, we encountered in several papers that become irrelevant when the scale is increasing, and as long as navigation technologies improve, the trajectory resolution increase. So we propose SaveDat. SaveDat is a platform for trajectories compression solutions. The platform has two modes, a silent mode and encode mode. In the silent mode, the server feeds a sample sub-trajectory sent by the client to a pre-computed trajectory patterns and validates the fitness of that pattern with a low-frequency updates from the client. In the encode mode, the server computes a lean model that's sent to the client for compressing its location data before sending it to the server. SaveDat supports a spatio-temporal trajectory and based off an historical trajectory to improve compression rate. Here we can observe a high-level overview of the server-client model as we implemented it. There are 4 channels between the server and the client, 2 for each mode. For the silent mode, 1 channel is for signals, which are data samples actually, and the other channel is for transmission frequency control. For the encode mode, 1 channel is for the encoded data, and another channel is for transmitting the encoder model from the server to the client. This is the basic architecture of SaveDat. The pre-processing stage has 3 main processes: data cleaning, data normalization, and data reshaping. The process trajectory is inserted to the trajectories DB and separated to a train and a test sets in a ratio of 70-30%. The train set feeding the model generator to train the RNN and the autoencoder. After the trained model transferred to the simulator to parallel to the test set. We chose to use an LSTM layers in our RNN, since LSTM is the best fit for our sequential processing needs due to the LSTM memorization property. The power of LSTM is by distributing its structure that regulates the flow of data. Here you can see that by supplying an input of n samples to the RNN, we are able to predict the following k samples. By that, we can make this process cyclic and feed the RNN with his predicted k samples, and we named it recursive RNN. We used the Haversine formula as our error metric. Haversine formula calculates the minimum distance between 2 points on a globular body by using latitude and longitude. The autoencoder model inputs n samples, and the output, which is predicted, are the same n samples. The uniqueness of the autoencoder is that the dimension of the input and output are equal, with a narrow layer in the middle of the model, which is less dimension when we compare to the input and the output. The autoencoder allows us to control the SNR, since the amount of dimension in the inner layer is controllable. In the autoencoder, we also use the Haversine formula as our error metric, just like in the RNN case. To increase our platform performance, specifically the compression ratio and the accuracy, we added another procedure before the model generator. In the trajectory DB, we cluster the trajectories by the k-means algorithms, and then we train the RNN model and the autoencoder model for each cluster. In addition, we trained a default RNN and a default autoencoder model for the whole trajectory DB. All of our experiments were based on the real trajectories dataset that captured on Route 101 in the United States by the NGCM program. The dataset contains about 4,800 trajectories with a sample frequency of 100 milliseconds. A major and a significant part of the experiment was the pre-processing and the compatibility measures for each model type. To be more specific, in the RNN case, we had two parameters, past and future. When past represents the amount of samples from the trajectory that was inserted to the model as input, and future, which represents the amount of samples that the model will predict as the trajectory's next samples. In the autoencoder case, the input and the output samples are supposed to be identical. Our first experiment's target was to locate the best value for future for the RNN model. We tested the presented parameter, past steps, future steps, mean error, compression ratio, and max error. And just as a reminder, the accuracy of GPS these days is 4.9 meters radius in non-urban environment and 20 meter radius in an urban environment. So we chose to fix the past parameter to 10 and start the experiment. As you can see here, the result, we chose the future parameter of 10 with a mean error of 4.8, which is better than the GPS accuracy. That will set us up with a compression ratio of 2. Here on the left chart, you can see the average error versus the future steps. And on the right side, you can see the compression ratio versus the future steps. On the left side, you can see the error histogram, and on the right side, you can see the loss per epoch. After one epoch, the model started to converge. The RNN achieved reduction of 50% of the trajectory data with an average error of loss of 4 meters. The recursive RNN rate was 7.58 meters, which is surprising, in fact, that the whole trajectory was predicted only with the first past samples. Here, the learning process is presented. Naturally, the first epoch has the best improved. Beside that, the learning process stops after the 7th epoch. Our second experiment target was to investigate the performance of the autoencoder compression with different bottlenecks. Giving 100 samples to represent a trajectory, we tried to compress it using an autoencoder, while the attempts include different input bottleneck proportions. Again, here we have the ability to choose the compression ratio and the mean error as we wanted. We set the input to a fixed size of 800 bytes and changed the bottleneck width. Here we chose the bottleneck of one, which gave us a compression ratio of 100 with a mean error of 34.9 meters. On the left chart, you can see the average error versus the bottleneck width. And on the right side, you can see the compression ratio versus the bottleneck width. On the left chart, you can see the error histogram, and on the right side, you can see the learning process with the loss per epoch. And again, after one epoch, the model started to converge. By using our proposed lossy compression algorithms, we have the ability to increase the compression ratio as we wish, but we will pay the error price tag. The platform experiment was on 4,800 trajectories and fully predicted 1,485 trajectories, which are 88% of the test set. The platform predicted 30 samples for every 10 samples, which is a save of 75% of the data and traffic. So, to summary, we've presented SaveDat and solution for trajectory compression. The platform saved up to 75% of data and traffic. The next step is to combine the RNN and the autoencoder to a hybrid solution. Thank you very much.